23 cluster. Now what happens is in the solutions when you are mixing these things, certain clusters form in preference to the other. That depends on the conditions. And molybdate, especially polyoxometalate, molybdate is a very interesting system in the sense you would have learned in your school the solubility of molybdate is much higher than that of tungstate. Okay? And that's why you see a large number of species with respect to molybdates. Okay. Now here for convenience I have put two of them, and in principle you can rationalize both of them. When I say minus water, there is a condensation. So there are two different sets of discrete species are forming, two different clusters. So in principle, I'll come back because somebody wanted to ask something. You can get, depending on the case, in principle you can have any one. I am just only showing 7 or 8, but you can have a variety of polyoxomolybdate structures, both isomolybdates and heteromolybdates. When I say isomolybdates, these are all isomolybdates, and when you say heteromolybdates, these are all heteromolybdates. There you have a heteroatom. It varies from case to case. Now, which one works? Many a time you only tell from the experimental data. Now, you take heptamolybdate solid, you put it in water, there is no guarantee the solution contains only heptamolybdates. There is a good possibility that you may have other species coming up. Now, what actually crystallizes is again depends on the other species present in that. Right? It is only you have to work out in a particular system, because when you are dealing with it, your phase diagram, because many a time these are all kinetically controlled phases, they need not be equilibrium phases. Keep that also in mind. Okay, now somebody wanted to ask something. Yeah.
Sir, how does pH actually controls the crystallization?
The pH control is only this particular thing. Here I am telling you this. This is not necessarily, a pH means many a time we think, at least I learned from my students, because many things we learn from students. It's not adding a, H plus or OH minus. In the case of copper sulfate itself, because of the nature of the metal hydride itself, because it is acidic, right? And there is going to be, it is competing with the water. That hydrolysis is going to vary. So the moment you disturb, that I told you already, the disturb by adding a little bit of ammonia or hydroxide or whatever it is, then the pH is going to change. It's not necessary you have to come to pH 7 or greater to have those hydroxy sulfate phases. You follow what I am talking about? Right? So in the naturally, because all of them are occurring minerals naturally, because we don't know the reaction conditions over there in the different geological area. But the beauty is nature tells you, minerals basically teaches you that there are certain equilibrium phases possible with respect to a few systems. It gives you an idea, but in actual practices, if you have to really do it in the laboratory, it is possible, but controlling is a little difficult. You have to be careful. It varies, depends on the concentration. Anyway, okay. Now coming back to this, so you get the cluster. Now I will just give you a small. I'm not going to take more than 5 more minutes, but you look at it. See here, you have, because this is a cluster. Yesterday I showed you Anderson-Evans cluster, so I want to only give that as an example. Here you have, you mix a chromium salt, sodium molybdate, and an acid. Okay, here you mix a complex, two separate solutions. It's basically for the solubility you are putting a methanol. Right? Now you are mixing it, now you are getting a particular compound. That compound, if you really look at it, this is a cluster. The cluster is coordinated with the copper hydrate. You understand? The reason why we have chosen a particular composition is because under these conditions, there is a guarantee of an Anderson cluster, a heteromolybdate cluster forming. Right? If you disturb it, things may go in a different way. Right? Now, what you have to remember is copper hydrate coordinates, then the remaining water molecules is only for packing purpose. And this cluster itself can get easily, forming the hydrated species. That's why you have a OH. Don't worry about it right now. Now the next one, similar composition, except that now you put a HCl rather than a acid. Instead of a weak acid, you put a strong acid. So when you do that, now what happens is the whole cluster changes. You understand? And now what happens is the cluster has changed. What is this cluster? This cluster is nothing but a MO36 cluster, but there is something interesting. This cluster itself is derivatized with the complex. Not complex, that ligand, the pyrazole. Right? And you have other, pyrazole which are protonated, comes as a counter cation, and this particular molecule, the particular solid forms. You understand? It shows the complexity of the system. What is important over here in comparison to the other thing? Over here and here, your copper doesn't figure in the product. You understand? The copper does not figure in the product. Now, the counter ion is the protonated pyrazole. Now, this is a little complex, but anyway, I have to complete the story. Now, over here, a similar reaction conditions, but in the case of different pH acetic acid, slightly different conditions. We will not get into the conditions. Now, what happens is you do have the Anderson cluster, but you form a new complex. The complex is a copper pyrazole connected with basically an oxalate. That is oxalate count. Only 1 minute. The oxalate is in situ form. Okay, and there are lots of literature. I will share this. You can read it later. There are n number of compounds which occur in the presence of an in situ formation of the oxalates. But whatever happens is at least our reaction conditions are controllable. So under these conditions, what happens is this cluster is condensing with the copper oxalate complex. Okay, these things are all reproducible. There is no problem. It may appear to be very complex species, but it's not really complex. In fact, if Professor Samejitra, when he shows much bigger clusters, they may look very complex. He goes to giant wheels and giant clusters, but these are all very simple, right? So the whole chemistry changes if you slightly vary the reaction conditions. Now, this is just a pathways, because how does acetic acid becomes a oxalate? Even we don't have any proof, and in all probability, a carbon dioxide is formed. We thought even carbon dioxide from the moisture, the amount is very small, the carbon dioxide. We tried to even use a carbon dioxide cylinder and then try to do the reaction, but we couldn't reproduce it. A carbon dioxide gets reduced. That carbon dioxide reduction is possible. What is driving the carbon dioxide reduction? In all probability, a copper, the pyrazole complex. But we were not able to prove it because we tried to do some experiments which we couldn't prove it, but we can make this compound anyway. And it forms this intermediate complex, and that complex condenses in that cluster. Okay, now, it's if you change the metal ion and the ligand, then you have a coordination polymer where the copper interacts with the azyl pyrazine complex from a coordination polymer, and this comes as only as a counter ion. When I say counter ion, then it's only a hydrogen bonding. This is the last slide, don't worry. And if you use a different complexing species, you can see it with cobalt and zinc. You get a hydrated complex. With a nickel, you get different species with the same crystallization condition. And with copper, two different species at the same reaction conditions. Meaning what happens is, in some cases when you are trying to prepare it, you can get a single phase, you can get a mixture of 3 phases or 2 phases. In principle, using powder diffraction, a technique called Rietveld technique, you can even estimate how much each one of these phases are present, provided you know the crystal structure of each one of them. So this is an idea. So most of the time when we make when you make a set of crystals, we not only do a single crystal, because single crystal there only you look at one crystal or a few crystals. We also look at the bulk, which is powder, and then we try to look at whether they match. Until you do that, because bulk is the reality. Single crystal is it may be lucky to have one. So the bulk is the reality. So we combine these things. So I think that's the end. So basically what I tried to tell you in the last 50 minutes or so is that when you do a reaction, it is very important for you to look at it, the kind of molecules which are participating in the formation of a particular crystal. And for this, you need to use a database to look at a series of structures already reported. Today, the database is large. That is why I gave this particular quotation from A.F. Wells in the beginning. The quotation now probably you will be able to rationalize it. At different stages in the development of chemistry, various compounds or groups of compounds have appeared to be anomalous as regards either their formulae or properties. When the appropriate advance has been made in, say, the theory of interatomic forces, or when a new technique has led to further information about the relative positions of atoms, it has become evident that the anomalies were simply indication of an inadequate understanding of the structures of the compounds in the widest meaning of the word structure. So today, whatever story I am telling you, tomorrow things may change. Maybe after 20 years, when you look at it, when techniques have become more advanced, you may have a different things. But basic chemistry will not change. Right? So next time when you grow a crystal, most of the time people will use the term recrystallization. In the supramolecular chemistry, especially when you are dealing with complex metal organic species, you have to be extremely careful. Not only metal organic chemistry, even organic chemistry it's a big problem. A good example is a benzamide. Benzamide is a crystal which is made by almost every organic lab. But today people realize that the benzamide has polymers. Depending on the way you crystallize, it's not necessary that you get the same compound. But the way we are taught in the colleges or in the schools, benzamide, you only look at the melting point. Many a time the polymers melting point may not vary. And NMR and other techniques, you only look at the molecule, you are not looking at the assembly of the molecules. So things can vary, right? So you can say you are able to recrystallize only your powder diffraction pattern of the compounds at different stages are identical. So I will stop here, and if you want to ask questions, please.
In the domain of polyoxometalates, what is the nucleation mechanism? Is it a one-step nucleation or a two-step nucleation?
See, crystals are not built molecule by molecule. You appreciate this? A crystal, a formation of crystal is not built of molecule by molecule. It's not that molecules, the bricks are, right? You have only a defined bricks. You understand?
Those bricks can be molecules, or what are the other?
It has to be molecule. Because of the solution, you are only dealing in terms of the molecules. You have to identify what are the bricks. You understand? If you are talking about a copper sulfate, then the bricks are copper hydrate and sulfate. The way the copper sulfate and hydrate aggregate, you understand? That aggregation, now to start with, for conveniently I put a hypothetical molecule called one copper sulfate, one sulfate, and forming a zwitterionic, a hypothetical species, as a brick. And you can consider that as a brick, there is no problem, because the composition is already defined. You have copper to sulfate 1:1, charge is balanced 2 + 2 minus, and then these bricks are going to be arranged. But the arrangement of the bricks, to take into account of both non-bonding interaction, that is hydrogen bonding interactions, and the close packing, you require additional water molecule coming inside. So now that bricks will be two. One is the copper sulfate species, a dimeric species, and a water molecule. Now if you want to say, no, I would like to do it in terms of three, no problem. You can think of copper hydrate, sulfate, water aggregating together. But for that aggregation of one particular crystal, how many copper hydrate, how many sulfate, how many water is required is a question mark. Okay. Now when it goes into a polyoxomolecule, now this is going to be much more complex. It's not easy to rationalize the phase diagram. But what you can rationalize it is under a reaction condition, some window, you know what is the kind of polyoxomolybdate species which are stabilized. All of them, heptamolybdate, octamolybdates, everything. In principle, you may have in a solution both hepta and octa. In fact, I asked some of the students yesterday in the posters. You can have, there is no guarantee that you, just because you take ammonium heptamolybdate and dissolve it, the solution is purely heptamolybdate. Right now, with the kind of techniques we have, it is difficult to show. In fact, Livache, a French scientist, unfortunately in all this system, we have no idea, no control of the solubility of a particular species. Because not all your compounds are going to be equilibrium phases. If they are equilibrium phases, then it is possible for you to measure the solubility. If they are not equilibrium phases, you have no way of knowing it. You understand? And in these cases, even getting that metastability region is difficult. But still, it doesn't mean it is completely hit and try. You know that in a particular cases, the Anderson clusters are stable. For example, the reason why we took chromium, because chromium will not interact with the ligand, and chromium is reasonably stable over the pH window we were using it. So Anderson clusters chromium is a predominant species in that range. So we were only varying the metal ions and the complex. So now what happens is, in our case, it is the Anderson cluster combining it with a copper complex. Whether the copper complex is a copper hydrate, copper pyrazole, or copper pyrazole also can have different complexing species, right? 1, 2, 3, 4. After all, you can write the equilibrium with copper 1 pyrazole, copper 2 pyrazole, copper 4 pyrazole. In few cases, we have seen it is copper 2 pyrazole also coming into picture. So it becomes complicated. You understand? So this is where the polyoxometalates are nice, but at the same time they are difficult because the number of species involved in the self-assembly process are too many. So everything depends on how you control the systems. Sometimes you become lucky, and many times it may be a futile attempts. So in fact, the number of cases we have, positive cases are very few. The failures are too many. This is because controlling the reaction conditions. I never talked about one aspect, that is temperature plays a role. So you have to have a really conditions. Many a time the crystals grow after 2 months or 3 months. Meaning what? That means it is quite soluble. If you try to hasten that solubility, meaning you give either you increase the temperature or decrease the temperature, trying to put it into a fridge, then competitive phases will crystallize out. You understand what I am saying? Because this is another problem. Then the type of complex you use, because the type of complex you use, it balances the solubility. Meaning there are some complexes which are less soluble, will precipitate immediately. There are some complex, basically you want the metal ion to be in the solution. That is the reason why you are adding a ligand, a complex, to make it in the solution. Otherwise, copper will precipitate as hydroxides or whatever it is, oxyhydroxides, anything can happen. So to keep a balance, so that these, you want the cluster to interact with the metal complex. But this is a game which is, it's a little difficult. But if you really want to, rationalize our reaction conditions, then you need to use. I will share some of the papers which we have written.